por el esfuerzo de hacer esta escuela. Yo lo he organizado algún año y es mucho trabajo, pero lo que han hecho ellos es exponencialmente mucho trabajo. Así que, Daniel y Luis, por no hagan caso, les agradezco de corazón el esfuerzo que han hecho porque es vital. Bueno, voy a empezar contando un poco lo que os espera. Y bueno, este es un curso de 8 horas, vamos a la clase de hoy. Oh, let me switch to English. Good point. The structure of the course is essentially 3 chapters. We have 4 lecture days, today, tomorrow, Thursday, and Friday. Yeah, and as Chema said, interdisciplinarity is something that we like here. And my course is not a course in a mathematical tradition. You have a course by Carolina Vallejo later in this high school. And she will talk about a classical theorem in group theory. Yeah, I'm going to touch several aspects of mathematics. And of course, doing this in 4 days, even if 2 hours, will allow me to scratch a bit the surface of the topics. Still, I think that the things I'm going to tell you will make you look at mathematical topics from a different perspective. So we will have kind of 2 blocks. The first 2 chapters, which refer to spaces, metric spaces, and properties of these metric spaces, and then a last part which involves operators, bounded operators in a Hilbert space. Okay. So today and tomorrow, and probably on Wednesday, I will finish chapter 1 and 2, and then I will start with operators and the relation between operators and groups and metric spaces in the last part of the lecture. My experience in the school is that people are very, do like the things, or teachers like the things they speak. But this is not always the case for the students. So I decided to do, as is typically done in universities, problems and exercises. Yeah, I will not do problems today, but problems and exercises allow to interact, at least with you, and I hope also with the people on the other side. Yeah, so I have prepared, and Daniel is going to send this by mail, but I'm old-fashioned, so maybe you can just distribute this, take one and pass it backwards. So today I'm not going to do exercises because we had the presentation and we don't have too much material, but maybe for tomorrow you can just take a look at exercise 1.5 because we are going to use it. I'm starting probably next week, depending on how fast I am today. I'm starting with this exercise today. So, and this is the opportunity to interact, to recap the things I am introducing, and so on and so forth. Okay. So, what do you need for this lecture? I told you it's a kind of mixed topic, and I'm going to need, from the algebra point of view, I need that you know what is a graph and what is a group. I'm not explaining it. I hope still not only in the exercises, but just interrupt me anytime, also on the other side. Yeah, you can send a message through the chat. There is somebody that will translate this for us. So interact. I'm not going to explain what is a group. I'm not going to explain what is a graph. I need from the analysis side that you know what is a norm space, yeah, a vector space with a norm. What are the axioms of the norm? What is a metric space? I'm not using it. If any one of you has problems, tell me. Yeah, and we can see what we do. I also need that you know what is a bounded operator in a Hilbert space. I'm not explaining it, but if you have problems, just let me know. So I hope you got some course in functional analysis. It's very basic what I'm doing, but I'm mixing from different fields. So what else? And of course, you have in the school other courses. I mentioned Carolina, and also Eva Gallardo is going to speak a lot about bounded operators. So take this as a prelude, if you want, of things that you are going to face later. And still, even if I will only scratch some of the topics here, I have prepared an ambitious proof, which is done at the end, and which is the relation between nuclearity and property A. So this is going to be advanced, and let's see if we can manage to do this proof, or at least that you get an idea, because this is related really to present day research. Okay, so I think if you don't have more questions, let me just begin with the main idea. Yeah, so chapter 0 is going to be very quick. Which is the intuition. And maybe this is the only thing that you will remember in some 5 or 10 years about this course, but still, it's not much. So what is large-scale geometry? What is the idea? So imagine that you have a galaxy. And if you like to look at stars and galaxies, you know that the galaxy is full of structure inside. Yeah, so you have solar systems, stars, many things. But if you move away from the galaxy and you look at faraway galaxies, and if you don't see very well, so if you have glasses and you go away, you take out the glasses, there is a point where you recognize that this dot there on the blackboard, oh, I should not go so far away from the microphone. I was just saying that far away, I just recognized one dot. Yeah. So this very big dot here is, and this is something that we are going to introduce today. It's not the same, but it's quasi isometric to a dot. Okay. So this is my abbreviation. We are going to have a lot of quasis in this first day. And this is quasi isometric to a dot. Another way to express this, so whatever is bounded, a galaxy full of structure, you forget about the local structure and you just see one dot. Now, this is the kind of equivalences we are going to be today. Another one. So imagine Z. The integers, we have 0, 1, -1, etc. Here again. And this is Z. And I move far away, take out my glasses, and I don't see dots anymore. I just see the real numbers. So again, we are going to prove this. This is just an intuition. You say that the integers and the real line are not the same, but are quasi-isometric. Okay? That's the main idea. So large-scale geometry is to look at spaces from far away. Let me just write down some remarks, and then I start with chapter 1, which is going to be more formal. I'm going to introduce formally what I mean by this strange idea and this quasi-isometry, etc. This way of looking at spaces is certainly not the one we are used to in the university. So local structure does not matter. Yeah. So there is no epsilon and delta. So continuity, if you ask a function to be continuous, you want to know what happens at that point and around that point. We are not interested in that. So epsilons and deltas, no partial derivatives, no directional derivatives, because this requires to know what the function is doing in one direction. We don't care about that in this frame. But don't relax, because we are going to have a lot of epsilons. Yeah. So I hope don't be so happy for the moment, because what matters here is what happens at infinity. Okay. So you don't care what is happening locally, but you do care that this space and this space have two ends. This is an invariant for the large scale geometry. Yeah, so you don't care around one point, but you do care what happens at infinity. How many ends do you have in your space? Yeah, this is an important notion. So we are going to have epsilons and ends all the time. Okay. What else? Cardinality is not an invariant, obviously. That's countable, that's not countable. And in fact, this is an example of something that changes a lot. Cardinality is a notion that is irrelevant for what we are doing in this course. Okay. And maybe I noted something else. And maybe yes, so cardinality is not an invariant by this example. And what I think is interesting from this large scale perspective is that we are going to look at notions that you know. Maybe some of you took a course on group theory and know that what a manifold is going to be tomorrow one important ingredient, and also property A, which is a more advanced notion, which is a generalization of amenability. And we are going to look at these old notions, amenability or property A, from this new perspective, large scale. And we will see that it fits very well with this notion. Okay. And an important part in this course is going to be the finite approximation. Yeah, this is going to be, if you want to put it in musical language, it's going to be a leitmotif. It will appear again and again. So finite approximations of the different structures we are going to deal. Okay, in the final part of this introduction, let me say that we are forced to have restrictions here. Okay? I cannot present to you the most general ideas. We are going to stick to quasi-isometries instead of the notion, which is the correct or the most general one, or at least the most general one I know, which is the notion of coarse equivalence. I will tell you quickly what it is, but we are going to stick to a special case. Yeah. My groups are going to be discrete and countable. Almost always finitely generated. So this is also a simplification, but I think it's a good one. Okay. And what else? I'm not going to prove everything, but I'm going to do proofs, and I just move some proofs to the exercise. Yeah, and if you have problems, I can tell you where you can find the proofs. The books I recommend are really very good. Yeah, and we can, if you have some doubts, you can contact me anytime. And yeah, I think that's all for the introduction. And let me now move to chapter 1. Is there any question on the main idea? Yeah, we are going to go back to this idea to look at spaces from far away soon. Okay. So chapter 1. Let me start maybe or begin with introducing a bit of notation and definition so that you see how I call the groups, what is a metric space, how I will denote all these things. Yeah. Definitions and notation. Okay, so let me start with an example. Okay, this is going to be a known space, and as an example, okay, this is a vector space. You have a norm, the axioms of a norm. If somebody don't know this, has doubts, just contact me. Okay, and let me give you an example that we are going to use at the end. Yeah, let me present for you as an example of a norm space. Maybe not the first one you would think, but this one that we are going to use in chapter 3, which are bounded linear operators on complex Hilbert space. Okay. What is the norm here? Is the operator norm. This is a linear operator in a Hilbert space. You can write it in many, many ways. You can take the soup, target vectors if you want. When you feed into the operation, just points from the unit. Oh, you can take points from the unit sphere if you prefer. There are many ways to say it. Well, this is actually more than a norm space. It's a Banach space because it's complete under this norm. Okay. So if the dimension of the Hilbert space is finite, and you want to fix on a normal basis, then this guy here, B of H, you can think of as matrices, call this M with complex coefficients. Okay? And the algebras of operators I have in my title are algebras that are contained in some B of H. Yeah? And the complexity that you can obtain working with operator algebras in B of H is huge. Yeah? And some of the notions we are going to introduce, nuclearity or property A for very concrete operator algebras, is going to simplify this complexity. Okay. Yeah. So if you fix on a normal basis in H, then you can think of an operator as a finite or infinite matrix depending on the dimension of your Hilbert space. Yeah, so IJ. So this is a matrix that reflects, expresses in coordinates. It's a coordinatization of the operator. Yeah, when you fix a base, it's like an abstract point in a manifold, and you can take coordinates and look at it as a row of numbers. Okay, and the connection will be, we'll meet this. We'll meet this in the last chapter, and yeah. Are you familiar with this example? Tell me. It can be infinite dimensional. In fact, it is the interesting thing, but we are going to approximate to matrices. This is going to be the Leibniz interface. Yeah, so it can be infinite dimensional, and then you have to think of this as an infinite matrix. Yeah, for instance, if some of you like mathematical physics, the canonical commutation relation of Heisenberg need an infinite dimensional Hilbert. We can discuss this on the breaks. Yeah, and in this case, the matrix is infinite.
But the basis of the space will be countable, or it can be not countable?
Yes, we are in a summer course. Of course, my spaces are going to be. So yes, complex, separable. Yes, I'm going to do the things not so easy, but not too complicated. Yeah. Okay, so metric spaces. How do I denote the metric space, which is going to be the main actor of this first chapter? So this is example A. Let me do B. Metric space. I denote with an uppercase X and Z. This is a more general notion than null space. You can do out of a null space a metric space. Yeah, by using, for instance, a distance between two vectors is just the difference of the norm. And we are going to introduce quasi-isometries. Let me tell you now what is an isometry, the plain one, the easy one. You have a map between metric spaces. Let me just say that I'm going to be lazy. Yeah? Usually you have to attach to the D denoting the metric, you have to attach which space you are measuring distances. I will forget it in a minute. Yeah, so I'm writing this in this example, and then I tell you that I will forget the index T, the X. Yeah, so this is a map between metric spaces. It's an isometric, it's an isometric embedding. Well, essentially, it does not change the metric relations between them. So you look at the distance of image points, and this is exactly the same in the distance of the domain points, if you will. Yeah, for all X. And I should say here, this is the metric in Y, and this is the metric in X. But if you look at the arguments, it's pretty clear where do they live. So I won't forget about these indices in a minute. Okay? Isometric embeddings are, of course, injected. And isometries are for me isometric embeddings with isometric inverse map. Okay, so F is an isometry if there exists if F is an isometric embedding with an inverse that is also an isometry and that composes with the F to the identity. And there exists inverse now y x isometry, isometric embedding, such that F composed with the inverse at x and the other way around. If I move first with that and then go back with the inverse. So it's a bijection. And this is the notion, isometry, and isometric embedding. These are the notions that we are going to relax, to formalize the idea of looking at spaces from far away. So this guy here is an inverse in exercise 5, wait, 1.5. When you see this, this is the pre-image. So if you want to solve, if you want to think about this exercise, think of this as a pre-image. It's not the inverse. Yeah. And what I'm going to tell you in a minute about quasi-isometries, so this guy here is a pre-image. Okay, so if you want to solve the first part, part A, think of this not as an inverse, could be an inverse, but in general it's not. It's just a pre-image. Let me, before I go to the definition of quasi-isometries, let me start again with one example. That's an important example. Countable discrete groups as metric spaces. Yeah, so groups appears in the title of the lecture, and here is the first reason why the groups are interesting. Okay, countable discrete . Okay, so I will denote groups with a uppercase G, and I introduce first what is known as a length function for a group. Yeah. So a function L from G to 0 infinity. So it's an attempt to measure the size within a group. Yeah, because we are going to look at groups at large distance. Now we are going to apply to groups these notions. Okay, it's a length function. If you satisfy a certain axiom, for instance, the neutral element. Yeah. If you are not so familiar with the language of groups, just let me know. Nothing. This is the neutral element has length 0. The second one, a group element and its inverse have the same length. Okay, for any G in the group. And the important thing, now there is something like a triangle inequality you have for rows, and you have for metrics of distances, is that the length of the product of two elements is below the sum of the length of these elements. Okay. And the prototype of what I have in my mind and will be very important in the course is the case of a finitely generated group. Yeah? So G I denote this by this. I denote this in this way. This means finitely generated. This guy here, the cardinality, this is my notation for cardinality, vertical. We are going to measure cardinalities of sets a lot. And I denote this by these vertical lines. And what do I mean by that? I just mean that any element of the group can be expressed as a bunch of letters in the generator set. Okay, so I'm going to give you an example of a length function in a minute. Yeah, I'm introducing an important notion for the course. Any G allows an expression S1, S2, yeah, where the little s are independent. Yeah, any group element is expressed as the product of generators. Give you two examples in a minute, and you will see that you already know these notions. Okay, and so in general, let me tell you, and there is in the book of Brown-Ozawa, there is a proof that any discrete countable group has a length function. Anyway, in particular, the finitely generated groups do have also a length function, which is just counting how many letters you need to express this. You may have many options to describe the same group element. And the shortest one is giving you the length function. So the length function of a finitely generated is just yeah, wait a minute. So you take the ends, you count them, how many letters you need to express this element, and then you take the mean. This is a way of expressing the length function. There was a question?
No, solo te he dicho yo que...
¿Cómo?
Solo te he dicho ínfimo, que igual hecho así.
No, era un efecto dramático. Yo el ínfimo lo pongo al final, pero si lo pones al principio, la gente se... Okay, so okay, so this is the length function. So this is an example, and we are going to use finitely generated groups almost all the time. It's one of the simplifications I had to choose. And let me also say that I will assume that this generating set contains also the inverse. Yeah, meaning if S is a generator, then its inverse is going to generate again. It's convenient. It makes my life easier. Okay, so what is the metric? Once you have the length function with the axioms, there is a canonical metric. And that metric is also important. It's the word length metric of a group. Yeah, so you can think of the group as a metric space. Yeah, and what is the metric? What is the distance between two elements in the group? It's just the length of G inverse H. Yeah, H in H in the group. Okay, and an important property which we are going to use tomorrow is the fact that this length is left invariant. Yeah, it's a left invariant. What do I mean by that? If instead of G and H, I use its translate, I just push or move And I don't see any difference between the distance between G and H and its translates. Yeah, for any in G. If I define the distance instead of G to the minus 1 H by G H to the minus 1, then I get also a right invariant metric. Yeah, that's a matter of chance. Also possible. Right invariant metric. Choosing L of G H to the minus 1. Okay, and the last thing, the last part of this long example are Cayley graphs. Yeah? Tell me.
We are using the neutral element as the zero because normally we will have then one because the neutral is only the neutral element.
Okay, yeah. Let me think. So what you need to know is that the distance between G and G, it's one of the axioms of a metric, is 0. The distance between one point and the same is 0. And here you use the condition that L of P is 0.
Yeah, I need the definition in the previous one.
This one.
When you define the word LP equals minus minimum of
Yes.
I mean, you put the neutral element.
Yeah, but the neutral element is never generated. Well, it's really not to generate the elements of the group. You can get it as S inverse S, so you can arrive it. But usually the neutral element is not in the generating set. Because generating sets and groups need to move the elements to get everything. Okay? Good point. Okay, let me just erase also this here. And I hope you can you hear me from the end? Can you hear me good? Okay, I hope there is no problem with the audio and we can continue. So a very nice way to think about a metric space is a graph. Yeah? And the distance is just what is the shortest path connecting two vertices of your graph. Yeah? So again, groups as metric spaces and groups as graphs. Yeah, when I say group, I mean finitely generated discrete countable groups. Yeah. Done.
Is the word length metric really a metric in the axiom metric space?
Yes. And this is linked to the axioms of the length function.
Yeah, I guess.
Yeah. So you can just check it. Yeah, and or try it, and if you have problems, we can discuss it. In particular, we will use the first important or first non-trivial proof today the triangle inequality of metrics. Okay, so groups as graphs. So you have a group, it's finitely generated. And in future, if I don't say anything, that's what I have in my mind. So what is the Cayley graph? Yeah? So what is the Cayley graph? Which is usually denoted by this. It's a graph that has vertices and edges. And you have as an exercise to compute the Cayley graph of a free group of two generators or the Cayley graph of a cyclic group. We can just catch up a bit more tomorrow. So what are the vertices? The group elements, okay? And when do I put an edge between two groups, two elements of the group? And you say that G is linked with H. Yeah. If there exists an S in the generating set that moves H to G. Yeah, very simple.
The notation is K of GS
K, yeah,
of
K
the,
graph.
of the group and of the generators.
Yes, you will see in a minute why.
Okay.
Well, there are many ways to denote it. This is one of the standard ones. If you like geometric group theory, and Diego probably will, you can look at this. In the new version of the summary of the course, there is a book by Clara Löw, a German mathematician, which is really, really nice for this part of the course. Yeah, it's a textbook and it's very explicit. And yeah, the important thing is that the Cayley graph depends on the generating set. Yeah, that's the point. Yeah. And so there is an edge between G and H if you can link them by one generator. Okay, let me just give you the standard example. Take G to be the integers. And let me take as generating set plus minus 1. I told you that I want to throw in, I write the group additively, and I want to throw in the inverse, just for the following reason. So you have here okay, so you have here 0, 1, 2. I can go from 0 to 1 with a generator. So I'm putting this here. Just by adding 1. And I can go from 1 to 0 by adding minus 1. But I cannot go from 0 to 2 with a generator. My generator is just 1. Yeah. And so you see you have both orientations. Yeah. And so the Cayley graph becomes an unoriented graph because typically in graph theory, you have both orientations. You just assume this to have a single edge. Yeah. So you have this here. You can link 0 with 1, 1 with 2, and so on and so forth. And to make clear that everything in the graph depends on the generating set, I'm going to give you the example, if you want, same group, different generating set. Same group, and take S to be of course, it's not a very clever choice, but you know mathematicians all the time think about strange things. And they don't relax with the obvious generating set, this one here, but they just try to make things sometimes more complicated. Yeah, and so here, if I draw the Cayley graph, put the 0 here, and then I can jump from 0 to 2, and from 0 to minus 2. And this is an unoriented, yeah? Let me just write here unoriented graph, just because my generating set includes the inverses. Yeah? So we can make things more complicated, but this is not going to be interesting for us in this course. Okay, I can jump from 0 to 2 and from 0 to minus 2. I can jump also from 0 to 3 and from 0 to minus 3. And from 1 to 3 and so on. And now you can just finish your picture Again. Okay. That's the same group, same dynamics, same way to push. You change the generating set. The Cayley graph of G with plus minus 1 is not isomorphic to this guy here. So as graphs, they are different, very different. One way, maybe you know that an invariant of the graph is the degree sequence. So you just look at the degrees, how many edges you have at each point. So this is a 2 regular graph. And this is a 4 regular graph. This cannot be isomorphic. Of course, number of little legs of edges that go out from a vertex depend on how many generators you have. Yeah, every Cayley graph is a K regular graph where K is just the number of generators. So these two are not equivalent. They are completely different from the point of view of graphing. And still we are going to, if you think again about this idea of looking from far away, if I go at the end of the lecture room and take out my glasses, I don't see what is the degree of a vertex. Yeah, I really don't see it. Yeah, and one of the things we are going to prove today is that this Cayley graph is going to be quasi-isometric. So this is really disgusting if you know what a Cayley graph is, that it depends on the choice of the generators. It's really disgusting. I'm telling you that maybe the notion is not, the graph is not, it's a very useful object, but it is useful when you look at it at large distance. Yeah, so this is the first example that tells you that these notions, quasi-isometries, are going to be useful. Yeah, because it's a kind of arbitrariness. Yeah, you get rid of the generators.
Una duda, si el cardinal del grupo generador es el mismo, ¿son isométricos o no? No tiene por qué.
¿Perdón?
Si el cardinal del grupo generador, bueno, del generador del grupo, ¿es el mismo?
No, yo creo que no, porque rompes la relación de adyacencia.
Vale.
¿No? O sea, tú tienes que el 1 y el 2 son adyacentes aquí, pero...
Vale, sí, vale.
¿No? Rompes, ahora no se me ocurre el invariante que estropeas. No tendrías el grado,
vale,
que es el más sencillo de los invariantes. No hay un invariante. Okay, good point. Yeah, let's go for let's go for the definition, the first important definition today, the next section, the notion of quasi-isometry. Yeah, in the exercise sheet, you will see that the first block is kind of gymnastics around quasi-isometry. Is there any question on this first part of notation and examples?
What do you mean by the two vertical parallel lines? The vision drawing.
Sorry? This here.
No, la de abajo.
It's maybe German. It's kind of saying, I'm very lazy. So, how do you write this? So you see, in the end, spend more time.
All right. Okay.
It was still on the notation part. So maybe I'm now too. Okay, so let's go for quasi-isometry. That's the first really important definition. We have said a collection of examples with which we can work. We have recognized a problem between Cayley graphs, taking different generating sets, and we are going to solve this problem. By the way, we are around 50 minutes. ¿Cuándo tenemos a 5, no?
Bueno, no sé.
Do you want me to make a break or no? Don't be shy if you feel tired. Now comes the important thing.
Era mejor preguntar, que levanten la mano los que piensan que esto y luego los que levantan la mano.
Esto es como en clase. ¿Quién va? So who wants to make a 5 minutes break? Okay, let's do 5 minutes. So I can erase the blackboard. I think it's, who wants to that I continue? No. Esto es como las elecciones. Okay, let's go for the first important definition here, which is the notion of quasi-isometry. And you have a map between metric spaces. Okay, and you call this map F is called bi-Lipschitz embedding. So that's the notion I'm introducing. Well, essentially what you want to estimate is the distance between the image points. Yeah? And before we had the notion of isometric embedding where the distance is the same. Okay. Now it's not going to be the same. And there is a constant mediating. Maybe you know it from function theory, what is Lipschitz. And as promised, I'm not writing here that this is a metric in domain and this is a metric in the image space in Y. Yeah, so you can just ask the arguments where is their metric living. Okay, so this is a bi-Lipschitz embedding if there exists a positive constant such that the distance between the image points is dominated from above and from below using a multiplicative constant in this way. Okay? And what is a quasi-isometric embedding? Well, it's essentially the same thing. You want to measure the distance between the image points. And now you allow a discontinuity. One of the important things here is that bi-Lipschitz embedding is always continuous. Yeah? So this guy here is continuous. So why is this? If the domain points are close, the image points are also close. Yeah? So it's a continuous mapping. A quasi-isometry is not continuous. So why? What is the new ingredient here? You have here a constant. Yeah? So you allow kind of jump discontinuities. A quasi-isometry or a quasi-isometric embedding is not continuous, yeah? In general. And this is not continuous. That's the new thing. But it's not too bad. We don't allow kind of infinite jump. Yeah, it's not continuous, but the discontinuity is not so bad. And here you have, well, this is a bi-Lipschitz, means from above and from below, and a quasi-isometric embedding is that there exists a positive constant and the b, which is bigger or equal than 0, such that this is 1 over c. Okay. This is the embedding. Yeah, remember I introduced the isometric embedding, and then I introduced the isometry. Yeah, the isometry had something to do with coming back. Yeah. This guy here, F, is Lipschitz equivalence. If it is a bi-Lipschitz embedding and you have an inverse, if F is bi-Lipschitz embedding, and there exists a G which goes back from Y to X, which is a bi-Lipschitz embedding, and the composition of both is the identity.
Igual el rojo no se desdespierta.
¿No? Okay. ¿El amarillo? That's continuous. No, continuous. Okay. So, which is now you learned the notation, no? Okay, such that the composition of these two, yeah, they are inverses of each other, yeah, and the other way around. G composed with F, Alex is X. So what is a quasi-isometry? It's essentially the same, but you will see them. Okay. We are doing coarse geometry. So you don't need class. F is a quasi-isometry. If it is a quasi-isometric embedding, okay, you have part I, and you can go back, and there exists a G, a Y to X, quasi-isometric embedding again, such that the composition is not the identity, but close to the identity, such that the composition is close to the identity Y, and the composition the other way around is close to the identity in X. Okay, and what do I mean by that? It's just that the distance, let's start here, of F. That means we test this to M such that the distance that's not zero. You don't have to land at the same point, but uniformly close to that point. Yeah, so this must be, yeah, and in large scale geometry, this uniform approximation uniformly over the whole space. That's the key notion. And you will see it again and again in any expression, definition, theorem, etc. Yeah, and you have also, this is of course distance of y, and you have the other way. That's there, y in the target space and any x in the domain space. Okay, so that's the notion. And we will start tomorrow by practicing a few examples so that you have a feeling of this quasi-example. Bueno.
En el caso de las lingüísticas es que se ve claramente que automáticamente son inyectivas.
Sí.
Pero en el caso de las cuasiometrías hay que pedir seleccionamiento.
No, es que las cuasisometrías ni son inyectivas ni son sobreyectivas, son un desastre. Pero por eso es que no lo son. De hecho, vamos. No, y además es que no podemos, porque entonces no hacemos, o sea, nos estamos, digamos, pisando a nosotros mismos. El problema es este. Bueno, me he cargado, ¿ves? No. So this is you don't have to. If I move on, if I move to the example, okay, maybe we can do an example now. Yeah. So the idea of being a quasi-isometry is that you can go from X to an f of X by F. And you can go back, but you don't go back to X. Yeah? You just go close to X. So you have a ball of radius m, and the only thing that you know is that with this quasi-inverse, that's the name, everything becomes quasi. Yeah? And the price to pay is that you don't have injectivity anymore. Yeah? And this guy going back can go back here, for instance. You don't go back to X, but over the whole space, you go uniformly close to X back. Yeah, that's the idea. Maybe a few remarks and then the example.
I don't know. Is the constant n important to be the same for the two, like the?
No, we have an exercise tomorrow, or maybe this. I'm not going to do all exercises, but you can take B and C to be the same. Yeah. So imagine that you have two different M1 and M2, and then you take the maxima, or the biggest one, satisfies the same inequality. Yeah. So it's not relevant the number. It's relevant that you have a finite number. That's the point. And here again, if B is bigger than C, then you can replace C with B. And so this is the solution to one of the exercises. Okay. Remarks. First one is obvious. Isometry implies by Lipschitz equivalence, implies quasi-isometry. Yeah. So if I put P equals 0, I get back the previous example. If I put C equal 1, I have an isometric embedding or an isometry. Okay. So these guys here are by Lipschitz. A by Lipschitz Equivalence is a homeomorphism. So everything which is open in the domain space is open in the target space. So this gives you okay. What else? I told you that in my course I will restrict to some cases, and let me now mention what is the most general notion. Yeah, the course equivalence. I'm not going to introduce it formally, but course equivalence, I want to mention it at least, so that you, if you read some books, you will see this word and then you know what it's about. Course equivalence. Just an idea. So here, if you want to put here's the distance between these two guys. The relation between the matrix in Y and the matrix in X is linear. So C times T. So if you take this as a kind of variable, plus B. So it's a linear relation. So you have the distance C times T plus B. If you want, it's a linear, not continuous. And the notion of course equivalence allows more general functions than this linear relation. Yeah, so a course equivalence means that you have maps, rho plus minus, from where the distance between these two guys is not sandwiched between these two functions. Okay, that's not very precise what I'm writing here, but the relation between the distances in the image and the distances in the domain need not be of this very simple form. Yeah, that's a quasi-isometry. It's enough for groups, enough for all the examples we have. At one point in the proofs I'm going to show you, I will tell you that we need a course equivalence. It's not quasi-isometric, but it's coarsely equivalent. So this is the correct notion in large-scale geometry. Okay, just as a remark. Okay, let's go for the examples I promised. Okay, any questions here? And I think many of the ideas that I have shown here will be more clear now. Okay, for example, we go back to this very initial example of Z and R. Let's do it formally. So imagine that you have Z, you have the integers, the even numbers, and R as metric spaces. Okay? And you take the Euclidean metric. So the first one you would think, and now I think it's quite clear that the even numbers can be embedded by iota 1 into the integers and then into the reals. Yeah, that's pretty clear. And that's an isometric embedding. Yeah, so these are isometric. The problem is how to turn back. You cannot turn back isometrically with the Euclidean. Of course, you can change the metric to how do you come back? It's G2 and G1. So that's the question. So let me just start here. This is R. Then I have put the 0 here, so you have the integers here. This is 1, this is 2, this is 3, and so on. And then you have the even numbers. So this is Z, and this is 2Z. So here you have 0, here you have 2, here you have 4, and so on and so forth. Yeah? And there is a pretty clear, you have to compress the whole, interval into a point. Here you can just send, if you want, you send the 0 down to 0, and the 1 down to 1. And everything that is in between you send to 0. Every real number, 0 and 1, 1 excluded, is sent to 0. Yeah, so this should be the G1 and G2. And so on and so forth. It's clearly a non-injective map. Yeah? In contrast to bi-Lipschitz embeddings and isometric embeddings. Okay? And here you do the same thing, but more modestly, because you don't have to. You just send 1 to 0 and 0 to 0, 2 to 2, and 3 to 2. How can you see it? You see it? Blue and yellow? Great. Yeah, and so what is the G2 function? It's an old friend in calculus 1, it's the floor function. Okay, and G1 of n is n if n even, and n minus 1 is n odd. And if you remember the definition of quasi-inverse, this G that goes back, the uniform, the m, is going to be 1. Yeah. So if you compose, I don't know, say I2 G2. So you start with a real number, you set it to the integers, and then back to the real number. And the worst thing that can happen here is distance 1. Yeah? Because you are uniformly far away from your target point. Okay, so that's, and you can do the same thing with 2. Yeah? So I1 plus G1 is again, yeah, not more than 1. So in this case, all the definition we have there, L is equal to 1. So what else? Let me, because I want in any case to prove for you that the Cayley graphs with different generating sets are quasi-isometric. Maybe let me mention one example where two spaces are not quasi-isometric. And then I present to you a proposition without proof. For me, it's in the exercises. You can just have some fun trying to prove it. It's also a standard proof, which is you can read in the Clara Durst's book. So this is example A. Let me mention, just not going too much into details, example B. I think I can squeeze it here. So imagine that you have a space which consists of all squares of natural numbers. Okay. So you have 1, and then you have 4, and then you have 9, and so on. What is important about this example is that the image points become more and more apart. Yeah, that's the point. And of course, X can be isometrically embedded into N or R if you want. Yeah, so this is an isometry, of course. But you cannot come back with a quasi-isometric embedding. Yeah? That's the natural candidate of the G function is that the composition of these two guys is not uniformly close, yeah, because it depends on how far away you are. That's not a formal proof. Maybe you can think of this example and ask me if you have some problems. So the distance, yeah, this guy here is not a quasi-isometry. The distance between G of n and G of n prime depends on where you are in n. Yeah, that's the point. But this example motivates the proposition I want to mention to you. Let me put the proposition here because this is an important definition. Proposition. One of the things, I myself not a super expert in large scale geometry. I'm learning this since a few years. But one of the annoying things is this quasi-inverse. Yeah, it's a bit boring. And now I give you a proposition that only uses an F. Yeah. So F between two metric spaces. Yeah, let me just not write formally. You can complete your notes correctly if you want. So let X and Dx be a metric space, Y be a metric space. Okay. So this guy is a quasi-isometry, even only if F is a quasi-isometric embedding with quasi-dense image. And what's that strange name? What does it mean? There exists an M, a positive M, such that the distance between f of x and y, oh, sorry, I forgot to quantify it. Sorry, such that for every y in the target space, there exists an x in the domain space, such that the distance between f of x and y is more or equal than n. Yeah. Yes, that's the way. Yeah. The proof is not very difficult. What is the advantage of that? I don't have a G. Yeah, I don't have any G. I can work everything with one F and the density of the images. Yeah. Remember again, this quasi isometries are not surjective, are not injective. So look at this example. From 0, I go to 0 to 0, but I do not hit all the real numbers course not. Cardinality is not an invariant, this I told you at the beginning. Yeah? And so let me just write a few remarks here. And then I go for the proposition I wanted to prove today in any case. And I think I can manage. Okay, remarks. Well, this proof is not very difficult. If you really understood what I raised here, the fact that if you do a loop, if you start with F and go back with G, if you assume quasi-isometry, you have an F and a G, yeah? Then it's not very difficult to see that you have a quasi-dense image. Yeah, you go back, but what you don't have in general, if you have a Y point in the target space, this guy need not be the image of somebody in G, in X, sorry. Yeah, this is not necessary. But still, around that point, you have an image point. Yeah? So again, the idea is you have X here, you have Y here, you have a yellow Y point, and you don't know if this guy is in the image, but you know it with a ball of radius M. Around that point, you have an f of x for sure. Okay. So this is quite easy to see. Names. If you read books, you will see the expression typical in coarse geometry. The image is an M net. Yeah, f of x is an M net or 1. Meaning just that for any point, you have a distance at most M, an image point. Yeah? So if you want, Z is a 1 net for R. Okay, so that's the image. The M is just the uniform mistake you do, or the price you pay is the uniform mistake you do if you replace isometries or bi-Lipschitz isometries or equivalences with quasi-isometries. Okay. And that's very convenient. In fact, in many books, the book of Novak and Yu, Guolian Yu is written this way. It's a very nice book. They start defining quasi-isometries directly with 1 mark. Quasi-dense. It's quasi-dense. It's not dense in the strict sense, but up to a uniform error. Okay, so let's go to the proposition. Okay. I'm a bit slower than I thought, but I think that's a natural principle. So in the end, I will ask you if the speed is okay. Can you follow all the time? Yeah. Proposition. Let's go to the Cayley graphs. Let's try to answer the question we raised. Yeah, what is important about the Cayley graph? It's large scale structure. That's the important point. Okay. And now we have the notion to prove this theorem. So imagine you have a group which is finitely generated. So it's prime. then being the same group, the map is obvious, it's the identity. I'm just measuring in different ways. Yeah? Okay, good. Then the identity up in G and V. What do you think? It's going to be a quasi-isometry, or even better, a bi-Lipschitz equivalent, or even an isometry? Split bi-Lipschitz. Okay. Then the identity is a bi-Lipschitz equivalent. Bi-Lipschitz equivalent. Which is a very special case of quasi-isometry with p equals 0. This discontinuous part is equal to 0. It does not appear in this example. So in particular, the Cayley graph of G and S is quasi-isometric. As I wrote for you in the beginning, you believe, now you know. Well, not now. I mean, hopefully. Okay. So, and you have two metrics. Now I'm going to attach the index S and S prime. That's not so obvious anymore. Yeah? What does it mean? I have a group element. So assume so a group element can be expressed in the alphabet of S or in the alphabet of S prime. And it may have different lengths in each alphabet. So this guy is going to be S1, for instance, Sn, or S1 prime, S, well, you, I1, IN. I don't have to take exactly the same ordering as in the generating set. Okay, forget it. J1, 2, 3, M, fine. And so I want to compare the distances in one and the other alphabet. Yeah, the observation here, let me just start the proof. The observation here is just that, of course, the identity sends G to G. And I want to see how can I really control this change of alphabets. Yeah, the observation is I can take the distance at the neutral element because of the translation invariance. Yeah, if you remember, the metric was G and H, whatever. I can just shift everything uniformly. That's the same. So everything, if I have this distance here between 2 points, G and H, this is exactly the distance in S, say S, for instance. Then I can multiply with G to the -1 here and here. So I can measure everything against the neutral element. Yeah? In fact, for a discrete group, the balls at G and the ball translated of radius R at the group point G and at the neutral element R have the same size. And you can just transport by environment. Okay? And now let me introduce the number that is going to help me for the bi-Lipschitz equivalence. Huh? So let me just, this is S prime, and I'm looking at the distance from the neutral element to a generator of the old or the first generating set S. Yeah? And I'm measuring this in S prime. if you want, this is the length function of S prime of S. And I do this for all generators, little s, lowercase s, and uppercase s. Okay, that's just a bunch of numbers, and then I take the max. Okay. So if you want, let me put this in a box. S1 is a group element, and I can express it in the old letters. In the new letters, I don't know, S alpha 1, S alpha 3 of the old letters. So in this case, if this is the shortest possible choice, the length of S1 in the new alphabet S prime would be K. Great. Now, so this is an important number because this is giving me the Lipschitz constant. Okay, and now I start computing. Let me just do some. Let me move here. And this is just triangle inequality. So I want to measure in the new metric S prime the distance between E and a certain group element G. Yeah. And the group element G, let me assume, let me write it here, assume G in the old alphabet is this bunch of letters. It's a realization if you want a minimum. Yeah, G can be expressed in S in this way. Yeah. And so I'm measuring this distance with respect to the new alphabet. So this guy here is E S1 Sn. Maybe there is a better way of indexing, but I think you can follow it. Yeah, I can put some indices and so on. Okay, I don't know how many letters. I don't care. But I use the triangle inequality of metrics, of this metric. I go from E to S1, and then I go from S1 to S1 minus S2, and so on and so forth. S1 Sn minus 1, and then I go to G, which is S1 Sn minus 1. That's and Sn. Okay. So this guy here is G. It's another way of writing G. This one here, and this one here, the first n minus 1 are the same. And I have translation invariants, so I can just cancel. I can just cancel this one with this one. Yeah, the yellow brackets. Sn is surviving. The same here. S1 and S1 appear in both arguments. Translation, left translation allows me to cancel. So altogether, I get distance in S prime of E S2 S dots, the distance in S prime E Sn. But all these guys are smaller than C, because I told you that the key guy is C. That's the maximum. So you get n times C. But n was the length of G. Yeah? If you want, this is C times the distance in S between E and G. This guy was N. So the assumption is here, this N is realizing the minimum expression, right? The word. And so, since everything is the same for S and S prime, I finished the proof, because you can do the same with the other generators. So this is the proof. And it's not only quasi-isometric, it's by Lipschitz equivalence, which is more. Yeah? And so looking at a Cayley graph, if you are disgusted by the fact that this depends on the generating set, then you take off the glasses, you think of the metric space, the Cayley graph as a coarse object. And then there is no problem with that. Okay. So maybe I still have 10 minutes. And I would like to start the last section of the first chapter. And then we start tomorrow at 11, I think. We start tomorrow at 11 with some exercises to try to fix the notion of quasi-isometry. A nice exercise is to show, for instance, that any finite space, any finite set is quasi-isometric to a point. This is my very first motivating example. And the isometry, well, you can think about it. There are not many possibilities. Yeah, you just think and we can comment it tomorrow. So, but let me just begin with section 1.3, which is the notion of growth of groups. Yeah, is there any question on that? Okay. Definition, I'm going to introduce two notions which are important in large scale geometry, and give you an example, and then I think I can stop. Yeah, that's the notion of properness, which tells you that the balls, we have metric spaces, we can consider balls, and these balls are finite. Yeah? This is the notion of properness. Bounded geometry means that not only bounded are the balls, but also uniformly bounded. Yeah? So these are the two notions I'm introducing. So a metric space XE is called proper. If for any x in the space and any positive radius, the number of the cardinality of the ball at x of radius r is finite. Okay. And a metric space is under geometry I will just denote it as PDD because it will appear a lot of times. If these balls are finite but uniformly over the whole space, and that's expressed with the soup. So imagine you may have finite balls everywhere, But somehow, when you go away from some distinguished vertex, you may have more and more and more plots. Yeah, that's for what we are going to do in this course very bad. Yeah, especially when we go to operators. Okay. So the example, in a sense, a prototype. Prototype. Oh, I think I forgot to say also. So this is the important notion, but I will. Let's not. Depending on which book you look. I'm also going to assume into the word bounded geometry that is uniformly locally finite. Yeah, this means just that I do not allow accumulation points. So the space 1 over n will not be bounded geometry. Yeah, okay. And so let me add it just for convenience. So when I state later theorems, I won't say bounded geometry. That's the key notion, that the balls are. Usually I will call this number NR, and that's finite. And I will also assume for hiding a notion which is not so important into the definition of bounded geometry, and uniformly locally finite. So there is and uniformly locally finite. By which I mean that the distance between 2 points in the space is bigger or equal than a certain positive constant. Of course, if the points are different. Okay. So spaces like 1 over n, I don't care. But don't take it too seriously. Yeah, that's not so important because from large scale geometry, if your space is not locally finite, you can change it to a locally finite one within the same isomorphy class. Okay, but so I don't want to write uniformly locally finite all the time, so let me just write this in bounded geometry. Important is the example, the prototype. That's important. Yeah.
Could you repeat the idea of being proper?
Being proper means that the balls have finite cardinality. So you have a metric space, you sit at a point X, you consider the ball around that point, and you have only a finite number of elements of the space inside.
I know you are talking about finite groups, but it was infinite unitary compact, because it's not an infinite space with the discrete metric is bounded.
Yeah, I see what you mean. That's not true. It's because remember what you need is finitely generated. You don't need a finite group. Of course, any finite group is bounded geometry, but every finitely generated group, that's my prototype, is going to be. So it's not the group what needs to be finite, but the generating set, because the metric is defined through the generator. You have finitely many, that's not. Okay, so let me give you the prototype, and then I because maybe you are mixing it with Lie groups, compact Lie groups. No, we are discrete. It's one of the simplifications of this course. Everything is countable and discrete. Okay, and for countable discrete bounded geometry is finitely generated. So here is the example. So this angle brackets means generated path. Yeah? So get accustomed to my notation. And of course, this is Esta minus. Okay. Then G with the generating set is bounded geometry. Okay. The first observation is we only need to show that the poles at the neutral element are bound. Yeah. So observation. By calculation invariant, need to show that so because this is exactly the same cardinality as the ball at G. So please check it. I prepared it for today, but we are almost at the end. Well, actually, we have 8 minutes, but you can just convince yourself that the uniformness, this uniform boundedness of poles is for free for groups because you can translate the poles everywhere and you don't change the cardinality. So it's enough to check that this guy here is finite at one point. Yeah, at the neutral end. Okay. So imagine that you have a group element which is in here. Yeah, and this group element is expressed as a certain generating set S1 as K, and K is below R. Yeah? K is below or equal to R. Yeah. So you can think of this ball like an onion, and this onion is built from surfaces. Yeah, so you fill from surfaces, so you have your neutral element here. Then you have the first sphere, which consists of the generators S1, Sj, whatever. Yeah. And then you have the second surface, which is the products S1, S2, whatever, Si, Sj. Si, Sj can be inverses or not the case. Yeah. And so what is the cardinality of this guy here? Yeah. Well, one, at least you have one element. It corresponds to the nucleus, if you want, the kernel of the thing of an atom. And then you have how many possibilities you have here. You have call the size, maybe call the size of the generating set n. And so you have n possibilities for the first sphere. And then you have n squared. Yeah. For this one here, because any letter in the generating set qualifies. Yeah, anyone. So you have by combinatorics, yeah, product rule, you have n squared possibilities. And at the largest sphere, you have n to the power 5. And that's a geometric progression. And you can sum this, it's obviously finite.
Pero ¿es igualdad o desigualdad? Tipo, como mucho será esto, pero no siempre será igual.
Todos.
Pero puede que uno se cancele con otro, ¿no? No.
Puede haber varias expresiones para el mismo elemento.
Entonces caes aquí. O sea, si caes, o sea, la bola se compone de la suma de las esferas, de los cardinales de las esferas. Los cardinales pueden ser menor o igual que n.
Sí,
vale.
Tipo,
Okay. Vale. Pero finito.
sí.
Entonces, so you have 1 minus. Okay. And that's fine. My picture was a 3 group. There you have the full ball. but that's okay, great. So you see, it's finite. It's finite, and by translation invariance, it's uniformly, the balls are uniformly bounded. And so this is really a prototype of a bounded geometry metric space. And the first time I recognized this, for me, I like groups since a lot of time, but this is really another way of looking at groups. It's metric structures of bounded geometry. And well, this is nowadays really very, very hot research topic. And I will finish chapter 1 tomorrow. But I will start by practicing properties of quasi-isometry, say half an hour. Discuss some problems and interact a bit more. And if you have some question tomorrow, you can state it in the beginning of the lecture. Okay, well, thank you very much.